Paging introduction. It is sometimes said that the operating system takes one of two approaches when solving most any space management problem. The first approach is to chop things up into variable size pieces, as we saw with segmentation in virtual memory. There is an inherent difficulties with this when dividing a space into different size chunks. The space itself can become fragmented, and thus allocation becomes more challenging over time. Thus, it may be worth considering the second approach to chop up space into fixed size pieces. In virtual memory, we call this idea paging, and it goes back to an early and important system, the Atlas. Instead of splitting a process address space into some number of variable size logical segments like code, heap, stock, we divide it into fixed size units, each of which we call a page. Correspondingly, we view physical memory as an array of fixed size slots called page frames. So we change how we allocate memory. So to avoid that free space on segmentation, we now only allow the process to access the allotted size for the process. So it allow us to do that using valid and invalid um, idea. So we just need to validate that and then invalidate the other's space. Therefore, we will be able to optimize the space using paging. So the crux, how to virtualize memory with pages. How can we virtualize memory with pages so as to avoid the problems of segmentation? What are the basic techniques? How do we make those techniques work well with minimal space and time overheads? So how do we virtualize it with the concept pages going back from Atlas to avoid the problem of free space? What are the techniques? What are the algorithm? What are the key ideas that we will implement to do this efficiency, space efficiency? So how do we make those techniques work with minimal space and time overheads? Simple example and overview. To make this, to help make this approach more clear, let's illustrate with a simple example. Figure 18.1, page 2, presents an example of a tiny address space, only 64 bytes total in size, with 4 16 bytes pages. Virtual pages 0, 1, 2, 3, 4. So you may wonder, how are we able to do divide that into 16 bytes pages or virtual pages? We will discuss that later. Physical memory, as shown in figure 18.2, also consists of a number of fixed size slots. In this case, 8 page frames, making for 128 byte physical memory, also ridiculously small. So we start with a small sample. So imagine this is the virtual page for the process. So this is the requested size of the memory, and this is the actual memory. So as you can see, we still have the OS reserved for the 0, but the pages are divided into this 4 separated, actually 3 separated rows. So this is how it looks like in practice, but as you can see, there is no unallocated space, unlike the segmentation. As you can see in the diagram, the pages of the virtual address space have been placed at different locations throughout physical memory. The diagram also shows the OS using some of physical memory for itself. Probably the most important improvement will be flexibility. With fully developed paging approach, the system will be able to support the abstraction of an address space effectively. Regardless of how a process uses the address space. So again, probably the most important improvement will be flexibility. With a fully developed paging approach, the system will be able to support the abstraction of an address space effectively. So this better abstract it. The physical frame were better abstracted using pages because there's no unallocated space, regardless of how the process uses the address space. So regardless how it is, these are divided in physical frame or how is this represented in virtual. We won't, for example, make assumptions about the direction, about the heap and stock grow and how they are used. So these are just a first simple example. We are not providing the direction of how the stock and heap grows or the direction of it. We're just worrying about how the process data will be allocated throughout the physical memory and how it will be represented virtually. Another advantage is the simplicity of free space management that paging affords. For example, when the OS wishes to place our tiny 64-byte address space into our 8-page physical memory, it simply finds 4 free pages. So again, another advantage is the simplicity of free space management that paging affords. So aside from not providing an allocated space, it also provides us simplicity for managing the free space. For example, when the OS wishes to place our tiny 64-byte address space into our 8-page physical memory, it simply finds 4 free pages. It simplifies 4 free pages. Perhaps the OS keeps a free list of free pages for this. So the OS just keep a free list of pages, and then for a 64-byte address space requested by the process, since we have this 128 allocate or physical memory, we know that those are divided into 8 pages. The OS already kept track of the free list out of that 8 pages. As we saw, the first frame or page frame are allocated for the OS and just grabs the first 4 free pages of the list. In the example, the OS has placed virtual page 0 of the address space in physical frame 3. So in this case, the OS allocated the virtual page 0, which is here, the 0, in the physical frame page frame 3. Virtual page 1 of the AS in physical frame 7, page 2 in frame 5, and page 3 in frame 2. Page frames 1, 4, and 6 are currently free. To record where each virtual page of the address space is placed in physical memory, the operating system usually keeps a per process data structure known as a page table. So to record this allocated space for the process, the operating system provide a per process data structure known as a page table, kind of like a PCV in the previous allocator or space management form or virtual memory form that we have discussed. It's important to remember that this page table is per process data structure. Most page table structure we discuss are per process structure. An exemption we'll touch on is the inverted page table. So all of the page table we discuss, including the page table in boot time, where we save all the trap into OS exceptions, are all a per process data structure, as well as a per page table for saving base and bound register. An exception for that is the inverted page table. If another process were to run in our example above, the OS would have to manage a different page table for it. Again, if another process were to run in our example above, the OS would have to manage a different page table for it. So if let's say we have allocated this already, if we want to add another process, therefore we have to put that on unused or unallocated, or the OS need to put that on unallocated so as not to overwrite those already allocated space, as its virtual page obviously mapped to different physical pages. Additional reason is that the virtual page for that are allocated to different page frame. So as you can see, as we have discussed, the library that allocates it tracks it using malloc library. So that malloc, since it is talking about a different virtual page, therefore it will allocate it in a different physical frame. That's just how it is programmed. Modulo any sharing going on. Now, we know enough to perform an address translation. Example, let's imagine the process with a tiny address 64 bytes performing a memory access. Move L with virtual address, comma, percentage EAX. Specifically, let's pay attention. Just a moment, guys. I'll just increase this size. Specifically, let's pay attention to the explicit load of the data from address or from virtual address into the register EAX. So let's say we're loading the virtual address to a physical memory. Let's not worry about fetching the instruction from process, just like we discussed in the previous video, where the kernel or the hardware rather fetch first the instruction to the process after it traps into the OS, and then convert it virtually and check if it has trap to handler exception. If not, it will load the data to the process. Here we're just talking about loading of data from address into the register EAX, and thus ignore the instruction fetch that must have happened earlier. And thus ignore the instruction fetch that must have happened earlier, which is that instruction we've talked in the previous video. To translate this virtual address that the process generated, we have to first split it into two components: the virtual page number and the offset within the page. For this example, because this virtual address space of the process is 64 bytes, we need 6 bits total for our virtual address. 2 raised to 4 equals 2 raised to 6 equals to 64. So again, to translate this virtual address that the process generated, so to translate this parameter in move L virtual address, or the virtual address to load into the physical frame, we have to first split it into two components, which called the virtual page number and the offset within the page. So this is the process of converting that into page type of virtualizing memory. So these are determined, of course, by the OS and the hardware availability. Let's say we have 128 kilobytes. Therefore, we divided it into 8 pages. So that also determine how we will divide this component, the VPN and the offset within this page. For this example, because the virtual address space of the process is 64 bytes, we need 6 bits total for our virtual address. 2 raised to 6 equals 64. Thus, our virtual address can be conceptualized as follows. So it starts with VA5 because just like any array or any memory or index array, it starts with 0. In this diagram, VA5 is the highest order of the virtual address and the VA0 the lowest order bit. So again, highest order. Again, the keyword is order. Because we know the page size 16 bytes, we can further divide the virtual address as follows. So we will start first with the number of bytes allocated by the entire process and then convert that into 2 raised to what. So from that, what would be the raised or the binary would it convert to? In this case, it's 6 bits, right? In this diagram, so because we know the page size is 16 bytes, we can further divide the virtual address as follows. So 16 bytes, how do we divide that into VPN and offset? So how did we know that it's 16 bytes? Because that's how each page virtual to page frame conversion was in physical memory. Now the page size is 16 bytes in 64 byte address space. Thus we need to be able to select 4 pages, and the top 2 bits of the address do just that. Again, the page size is 16 bytes in a 64 byte address space. Thus, we need to be able to select 4 pages. And the top 2 bits of the address do just that. So to be able to 64 divided by 16, let's try. Yeah, it's 4, right? So therefore we need to select to be able to select 4 pages, and since we minus that 4 to 6, therefore we use the top 2 bits of the address. So thus we have a 2-bit virtual page number. So the offset tell us where inside the page a byte lies. So this offset determine where in this page lies. So let's say we have this page frame 7, like 111. When we add the offset, let's say we have an offset 5, we get 117. That's the exact byte in physical, or that's the exact physical address of our virtual address. So that's how actually we convert that to memory from virtual address. If the page size equals to 16 bytes, then we must be able to select any of those 16 bytes positions. Number of unique positions equals to 16. So how many bits do we need to represent 16 distinct values? 4. So that's actually the reason it's not 64 divided by 16. Okay, so it's just the bits that we need to represent 16 distinct values. So it's 4. 2 raised to 4 equals to 16. So 4 bits are required to count from 0 through 15. So the 16 possible byte positions. Since each frame, as we can see here, has 16 bytes, right? Because it's divided in 1, 2, 3, 4, 4, 16 bytes. So the way to represent that is 4 bits to count from 0 through 15, which is the 16 possible byte position. The remaining bits tells us which byte of the pages we were interested. The remaining bits tell us which bytes of the page we were interested in. 4 bits in this case. We call this the offset. So the first VPN is the virtual page number. So this will be determined. This will determine the physical frame position, and then we just need to add this to get the actual physical address. When a process generates a virtual address, the OS and hardware must combine to translate it into a meaningful physical address. For example, let us assume the load above was the virtual address 21. So we now input the movl21 percentage EAX. So that's how we load this into physical memory. So where that this actually goes in the actual physical address. So turning 21 into binary, we get 010101, and thus we can examine this virtual address and see how it breaks down into a virtual page number and offset. So 01010101. So that 21, when we convert to so that's the virtual address 21. So how do we convert that on the physical address? Where does that 21 actually goes when we load that? Here is what will it look like. We convert that into a binary. Thus, the virtual address 21 is on the FIP 0101 byte of virtual address page 141. So why is that? Because 01, so we know that we have 0 to 64 bytes address space. Now, we're talking about the virtual address 21 of this process, where that byte actually goes in the physical address. So these are the answer. Turning 21 into binary form, we get 010101, and thus we can examine this virtual address and how it breaks down into a virtual page number and offset. Thus, the virtual address 21 is on the FIP 0101 byte of virtual page 01. So it's in the FIP of the virtual page 01. So these are the virtual page 01, which is here. When we combine it, it's actually in page frame 7. So page frame 7, how do we convert that in binary? It's actually this. Thus, the virtual address 21 is on the FIP on the byte of page 1. With our virtual page number, we can now index our page table and find which physical frame virtual page 1 resides within. So we can now check the page table, which from that is 21 of that process, the 21 byte of that process, which where it located, or where was it allocated by the OS in a page table. So we were gonna index that to find it. In the page table above, the physical frame number PFN, also sometimes called the physical page number or PFM, is 7. So the physical page number for that, so we convert this virtual physical number into its physical page number or PPN, which is 7. So here, page frame 7, and it's a binary 7 7. So when we convert that 7 into binary, we get 111. Thus, we can translate this virtual address by replacing the VPN with the PFN. So we will replace this VPN to VPN of 111 and then issue the load to physical memory in figure 18.3. PFN is not necessarily the same number of bits as VPN. Again, PFN is not necessarily the same number of bits as VPN. PFN, physical frame number, depends on how many page frames exist in physical memory. So because we have each page frame in the figure, physical memory has 8 frames, frame 0 through 7. To index 8 different frames, we need 3 bits. Since 2 raised to 3 equals to 8, that's why PFN equals to 7 is written as 111 because 3 bits are needed. So to that's where the 111 came from, because we have 8 frames, so 2 raised to what, that will determine the number of digits we have as 7. So because 3 bits are needed, if PFN were only 2 bits, you could only represent 4 frames, 0 to 3, but the diagram shows 8 frames, 0 to 7, so you need 3 bits to cover all. So this PFN is 7, so these are the translation. Instead of concatenation, you can also think of it as this: physical address equals to PFN, the physical page number, frame number, times page size plus offset. PFN is 7, page size is equals to 16, offset equals to 5. So 7 times 16 plus 5 equals to 1112 plus 5 equals to 117. So as shown here, we can see that it starts with 1112. So plus 5, which is the offset, which is these are the 5 offset. So this 0101 is converted as 5 in binary, right? From binary. So VPN equals to 2 bits because 4 virtual pages. PFN equals to 3 bits because it 8 physical frames. So we convert that 2 bits because initially it has 4 virtual pages, and we convert that of 3 bits because it has 8 physical frames. That's why PFN equals to 111, 3 bits, not just 2 bits. So VPN 2 bits equals, select which virtual page. PFN 3 bits tells you which physical frame. Offset 4 bits, which byte inside the page. So which byte that 4 bits is. So the final physical address has VFM, which is 3 bits, plus offset 4 bits equals to 7 bits total. Note the offset stays the same, like it is not translated because the offset just tell us which byte within the page we want. Again, note the offset stays the same. It is not translated because the offset just tells us which byte within the page we want. So the offset is not translated, unlike VPN, because it's just part of the page, physical page frame or virtual page to physical frame that we want. It's just part of that. It's a spatial location from that. Our physical address is 111.0.1.0.1, 117 in decimal. So when we convert that 111.0.1.0.1 binary to decimal, it's actually 117. And it's exactly where we want our load to fetch data. So that's where we want the byte 21 to load exactly in the physical address from figure 18.2 page 2. With this basic overview in mind, we can now and hopefully answer a few basic questions you may have about paging. For example, where are these page tables stored? What are the input what are the typical contents of the page table? And how big the tables? Does paging make the system too slow? These and other questions are answered, at least in part, in the text below. Read on. So we're gonna answer where are these pages are stored. So how does the OS track this allocated space, and how does it convert that, just like in the previous video? How does it allocate and convert that in a virtual address space? How does it fetch and load it? How does it drop into the OS? What are the typical contents of the page table? How does the code, heap, and stock are implemented in this? How does it how does it avoid free space, right? Does the paging make the system too slow? So does this new process make the system too slow compared to the segmentation, virtualization of memory? So this will be answered in the next section. So where are pages tables stored? So pages can get terribly large, much bigger than the small segment table or base or bounds pair we have discussed previously. So the small segment table that used to track the free list, we discussed the node underscore data structure earlier, the size, the header, as well as the allocated size, and the code for that was actually smaller than this, because these pages could be terribly large. For example, imagine a typical 32-bit address space with 4 kilobytes pages. So let's say we're allocating a 32 bits address space with the 4 kilobytes, or divided into equally in 4 kilobyte pages. The virtual address splits into a 20-bit VPN and a 12-bit offset. Recall that 10 bits would be needed for a 1 kilobyte page size, and just add 2 more to get 4 kilobytes. So a 32-bit address space means every virtual address is 32 bits long. So that gives 2 raised to 32 possible byte addresses. So equals to 4 gig virtual memory. So virtual address equals to 32 bits. So earlier we have an address that is 16 bits. So here, 4 kilobytes, for example, is 4096 bytes. How many bits to index inside 4096 bytes? 2 raised to 12 equals to 4096. This is how we get the 12 offset bits, because we find its binary form. So this is where that 20 bits or the VPN actually located. So here, total address equals to total address bits is equals to 32, offset equals to 12. So 32 bits address space, it's earlier we discussed a 6 bits address space. Now we're talking about 32 bits address space, a 12 for its offset, a 20 for its VPN. So 32 minus 12 is equals to 20 bits. So what does that entail? So for 64 we need to raise it to 6 times to get 6 bits as an address space. So 2 raised to 32, what does that give us? It's a 4 gig virtual memory. So now we're talking about allocating. Let's say a process wants to get a 4 gig memory. So this is how it looks like. And this is why pages are actually big. So here, VPN equals to 20 bits, offset equals to 12 bits. So there's a virtualization of that. Physical memory, 64 kilobytes. 32-bit virtual address, 4 kilobytes pages, 20-bit VPN plus 12-bit offset. So frame 0 equals to page table, frame 1, 2, so here. So these are the realistic view of an operating system where the frame, so it doesn't matter where in memory, it doesn't not matter to, just because it's 0, the frame is 0, although the OS data is always at the start of the physical memory. But just because it's always at the start does not mean that the meaning of this frame is at the start. We're just dividing it into 16 frames. So frame 0, frame 1, frame 2. And also so that we can get a gist of how the OS kernel, OS data, and page table are divided. So they can be in separate frames. So a 20-bit VPN implies that there are 20 to 20 translations that the OS would have to manage for each process. That's roughly a million, assuming we need 4 bytes per page entry or PTE to hold the physical translation plus any other useful stuff. We get an immense 4 MB of memory needed for each page table. So for the OS to track each page table or each pages, which is the 4 kilobytes. Let's see how many kilobytes is that. Yeah, for 4 kilobytes per page. So for 4 kilobytes, we need a 4 MB of memory. So just to store, that's how big it is, because the OS needs to create a 20 translation to translate that VPN into an actual physical frame to be able to allocate and track it, because this page table are using is being used by the OS to track the currently allocated processes. So that is pretty large. Now imagine there are 100 processes running. This means the OS would need 400 MB of memory. So let's say 4 kilobytes per process. For 4 kilobytes, they have 4 MB. So let's say you have 100 process. For that alone, you need 400 MB of memory just for all those address translation from virtual memory. That's why we don't use this page table as is. We created an algorithm which we will gonna discuss in the future, called TLB. So that's like a translation guide or algorithm that again will be helped by the OS and hardware combination to make those translation efficient using this page table virtual form. Even on machines with gigabytes of RAMs, hundreds of MB just for page tables is very wasteful. This is exactly why OS designers introduced multi-level page tables and later inverted page tables, hash page tables, to avoid allocating a giant flat 4 MB table for every process. So this is why we have multi-page table, inverted hash page table. So we have different kind of table, or the OS designer created that because of this huge memory consumption of the table. Though it minimized the unallocated space, just for translation, the OS consumed those. That's makes it inefficient. So to solve that, there has been different page table or the data virtualization form and algorithm that has been created. So each page needs an entry in the page table. So to for OS to allocate the pages in its page table, it needs an entry in the page table. So if we assume 4 bytes per PTE, enough for the PFN plus flags, that's 2 raised to 20 times 4 bytes equals to 4 MB. So each page actually needs an entry, which is called PTE. So let's say that's 4 bytes for in every per PTE, and now for PFN plus plugs. So that's 2 raised to 20 times 4 bytes. So 2 raised to 20 is the VPN, the binary of VPN, times 4 bytes equals to 4 MB. So each process needs 4 MB of memory just to store its page table. So the reason why it's 4 MB because of this, we got 2 raised to 20 times 4 bytes. And then these 4 bytes is the PTE, or process table entry. So we multiply that by the VPN, the binary of VPN times 4 bytes, and we get 4 MB. So each process needs 4 MB of memory just to store its page table. 32-bit virtual address, 42 kilobytes page size, 2 raised to 12 equals to 4096 bytes per page. So this 2 raised to 12, we get 4096, so that's the offset, binary of offset, which is the 4 kilobytes. So that's how much allocated per process. So leaves 20 bits for the VPN virtual page number. So each process has 2 raised to 20 equal 1 million virtual pages to potentially map. So as you can see, when you raise it to 20, it has a 1 million virtual page. So since we have 32 bits address space, for 64 bytes, let's divide that 2 raised to 32. That would be, let me just compute that. Two raised to 6. 2 raised to 6 equals to 64. So that's the allocated space we have. How about 2 raised to 32 equals to 4 gig. So in that 4 gig, we actually have 1 million virtual pages. No, 4 gig, let's see, 4 gig of memory. Yeah, so 4 gig of memory would have, if it has a 4 kilobytes per page per process, it has a 1,000 process into this 4 gig of memory allocated. So that's what it maps. So if the OS is running 100 processes, 100 times 4 MB equals 400 MB. That's 400 MB of RAM consumed just for translation structures, not program code or data, as we saw, because that's consume most of the process or the memory. Because page tables are so big, we don't keep any special on-chip hardware in the MMU to store the page table of the currently running process. Instead, we store the page table for each process in memory somewhere. So we didn't use an on-chip, just like the cache in the CPU that we discussed in the previous video, because the page table are so big it can't handle that. Remember, cache is only so fast if it's small. So we store that page table for each process in memory somewhere. So if we can allocate that 4 gig, we maybe have 16 gig of RAM. So we chop some of that 16 gig of RAM to allocate this 400 MB for this page table. So let's assume now that page tables live in physical memory that the OS manage. Later, we'll see that much of OS itself can be virtualized. Again, later, we'll see that much of the OS memory itself can be virtualized, and thus page tables can be stored in OS virtual memory. So let's say first, let's imagine that we're actually putting that in a physical memory. So though it's big, it's chopping a lot in our 16 gig RAM. That's enough for now, but later we will later realize that we actually store that in a virtual memory and even swap to disk, but that is too confusing right now, so we'll ignore it. In figure 18.4 page 5 is a picture of a page table in OS memory, the tiny set of translations in there. So 3752. So later we will discuss how TLB virtualize that. So how's that algorithm virtualize the memory. So how we use cache to virtualize this page table to make it efficient. So we don't have the free space problem of segments, and we solve that using we add the cache later on TLB to be able to use this page concept or page from Atlas efficiently. So what's actually in the page table? So let's talk a little about page table organization. The page table is just a data structure that is used to map virtual addresses, or really virtual page numbers to physical address. So just like the data structure we used in node underscore struct earlier, that also has a size like header underscore t to make the free space management efficient for segmentation. This pages is also a data structure like that. So again, in computer science, it all boils down to data structures and algorithms used to manage the bits or the assembly code and bits of the actual CPU and memory. So the page table is just a data structure that is used to map virtual addresses. So it used again to map virtual addresses to convert it to physical frame, or really virtual page numbers to physical address, physical frame numbers. Thus any data structure could work. So any data structure could work because it's just used to map it. The simplest form is called a linear page table. So again, it's a data structure which is just an array. So here, an x86 page table entry. For now, we'll assume this simple linear structure. In later chapters, we will make use of more advanced data structures to help solve some problems with paging. So this simple or array data structure to represent these pages to virtualize memory are just its simple form. Later, we will discover an advanced data structures and algorithms that will allow us to solve some problems with paging. So to solve this paging, again, we will gonna use cache for that to be able to not store that in memory, but be able to use like cache to be able to not access memory because it's slow using page table to be able to serve the request faster, but also at the same time reduce the free space issue of segmentation. So as for the contents of each PTE or page table entry, so this is the 4 bytes that we have that we multiply by the binary of that VPN. which is the 20. So that VPN, this is the where the conversion is happening, because we need to convert this data to be able to map it into a physical frame. So in that physical frame, that will determine if it can access or not, or what are the things that we can cache or not. So here is the example of this data structure. Again, it boils down to just a data structure or a code that we can manipulate using functions that we can add features and so on. For now, we will assume the simplest linear structure. In later chapters, we will make use of some of more advanced data structures to help solve some problems with paging. As for the contents of each PTE, we have the number of different bits in their word understanding at some level. Again, for now, we will assume this simple linear structure. In later pages, we will make use of more advanced data structures to help some problems with paging. For the contents of each PTE, again, for now we will assume it's simple. Again, as for the contents of each PTE, we have a number of different bits in their word understanding at some level. A valid bit is common to indicate whether the particular translation is valid. So in this 4 bytes of page table entry, a valid bit in there is where we allocate or unallocate or resolve the segmentation problem of unallocated pre-space. For example, when a program starts, a valid bit is common to indicate whether the particular translation is valid or whether the programmer accessing a valid data for it. For example, when a program starts running, it will have code and heap at one end of its address space and the stock at the other. So does that cover or does that valid allocation for this specific scenario? All the unused space in between will be marked invalid. So that's where the page table data structure are for, so that all those invalid bit will be allocated or will be free to be allocated on other processes. And if the processes tries to access such memory, it will generate a trap to the OS, which will likely terminate the process. Thus, the valid bit is crucial for supporting a sparse address space by simply making all the unused pages in the address space invalid. So this is how it supports the address space, by simply making all of that unallocated that used to be between the heap and the stock invalid. We remove the need to allocate physical frames for those pages and thus save a great deal of memory. It means the OS can keep the virtual pages space sparse, lots of unused virtual pages with no physical backing. So physical memory is only allocated for the pages the process actually uses. So this is what this is how it solved the segmentation problem. It only allocate physical memory or physical frame to the process that actually uses it. It doesn't provide any unallocated spaces, which makes it efficient. Instead of wasting RAM on pages the program never touches, just mark them invalid in the page table. So this is what the PTE does. That's why it needs the translation. But it costs a lot. So how do you optimize this? We will use a cache to optimize this. So the page table are needed, of course, but using cache later, which we will describe, solves this issue. So we just mark them invalid in the page table, because again, OS actually mark that or remembers that using the page table, the allocated and the unallocated virtual space. Physical frames are allocated only when the program actually uses that page. Segmentation. Segmentation save memory by not mapping the big unused region between segments. Paging with valid bits saves memory by not mapping unused pages to frames. So that's the difference it has with segmentation. Again, segmentation save memory by not mapping the big unused region between segments. So actually, it doesn't map the unallocated or segment region. So it's a data structure that did not allocate that. But at the same time, it has a problem with the free list or the scattered free space in memory. But paging with valid bits saves memory by not mapping unused pages to frames. So it doesn't map it in the first place. So this is the different of this data structure. It doesn't map that in the first place, and it doesn't have this. You don't need this scattered data structure or that free space, because again, it has a fixed size. So instead of that, you have this fixed size. Since you have a fixed variable size allocation or pages allocation per process, you now have therefore not have to worry with that unallocated sizes or non-contiguous allocation. Again, we still use the array here, so it requires a contiguous data. But because we only allocating fixed size with this new concept of page table entry that is mapped to the page table and then converted based on the number of frames using VPN and offset, we therefore solve the issue of segmentation. So here's an example. Without a valid bit, you frame. So with a valid bit, invalid, invalid, invalid. So these are the graph of that for the food for thought. So we also might have protection bits indicating whether the page could read from, written to, or executed from. So this bit, so a little bit of memory, it could be tracked as well in page table, whether that could be read, written, or executed, just like in the segmentation concept, where the code could be read and executed, while the heap and stack could be written and write too, because those are dynamically changing throughout the lifetime of the process. So this is how we implement this in a page data structure. Again, accessing a page in a way not allowed by these bits will generate a trap to the OS. So since it's in a page table and the trap or the return or exception handler of OS is also in a page table, once you access this or that part of memory, it will generate a trap to the OS. There are a couple of others bits that are important, but we won't talk about much for now. There are a couple of other bits such as this. So a present bit indicates whether this page is in physical memory or on disk, i.e. it has been swapped out. So those are just like the things you use to track where those are located in whether it's physical bit or in memory, that is used by the OS to track what is that data for. We will understand this machinery further when we study how to swap of the address space to disk to support address spaces that are larger than physical memory. Swapping allows the OS to free up physical memory by moving rarely used pages to disk. So again, when we study how to swap parts of this address space to disk, so this address space, let's say 32 bits address space, which like 4 gig allocation, how to swap that to this to support address spaces that are larger. To support an address spaces that are larger than physical memory. So how do we support an address space that are larger than physical memory? So we will put things that we're not currently using from memory to disk to swap it so that we can use other things in memory. We will discuss that in the future. So swapping allows the OS to free up physical memory by moving rarely used pages to disk. A dirty bit is also common, indicating whether the page has been modified since it was brought into memory. So those are as well are mapped into data. So everything boils down to data, guys. As well as this bit, like the for page table entry. So these are used to track the dirty bit, whether it has been modified upon entering the memory. So a reference bit, aka access bit, is sometimes used to track whether a page has been accessed and is useful in determining which pages are popular and thus should be kept in memory. So this is also a data structure in code that used to reference or to track whether a page has been accessed. So we use if-else statement here in the background and are popular and thus should be kept. All of this we use an if-else statement and thus should be kept in memory. So whether has been accessed. So this is how this bit of a page table entry or of this data structure is what we're gonna use to solve this issue of page table. So we will use this as a cache. So access bit, if it's accessed already, therefore we will put that in a cache of the CPU, which we'll discuss in the previous video, and in the memory as well, so that we don't need a page table to access that. So we can serve the access faster. Thus should be kept in memory. Such knowledge is critical during page replacement, a topic we will study in great detail in a subsequent chapter. So figure 18.5 shows an example of page entry from x86 architecture. It contains a present bit, read or write bit, which determines if writes are allowed to this page. So if writes are allowed to this page, or the allocated memory for the process, which determines if a user or supervisor bit, which determine if a user mode processes can access bit the page. So this data structure as well also has this user or supervisor. So this is how it implements the user and kernel mode for each program. A few bits WT, PCD, PAT, and G that determines how hardware caching works for these pages. So a few bits PW, PCD, PAT, and G that determines how hardware caching for these pages. So this data structure determine how it will handle the hardware caching, or in the CPU or in the previous chapter for these pages, an access bit and a dirty bit. So an access, so that's how we use the caching, and a dirty bit if it has been modified. So that's the way we track the data or bit in this data structure if it's modified upon entering. So the page frame number itself, so the PFN itself is included here. Notice it's not doesn't have this the PFN. This is the converted already from VPN. So that's the physical frame table. So this is also how to track, kind of like of the header or the size of in the segmentation. So read the Intel architecture manuals for more details on x86 paging support. The hardware architecture, CPU plus MMU, decides the possible page sizes. So again, the hardware architecture, CPU plus MMU decides the possible page sizes. So the CPU that you have and the MMU will actually decides how the page size. So in this case, it has 4 kilobytes. Example, x86 traditionally supports 4 kilobytes pages plus larger huge pages 2 MB 1 gig. So you may wonder, how do we determine the page sizes? It's actually determined by your CPU, because again, it's also this data structure or the page table could be used as well to handle the cache in CPU. Therefore, the combination of CPU and memory management unit or MMU decides the possible page sizes. Example, x86 traditionally supports 4 kilobytes pages plus larger huge pages 2 MB 1 gig. The operating system chooses which of the supported sizes to use. So the operating system chooses which of the supported page sizes to use. So the OS now will dictate which the page sizes to use on that CPU plus MMU available page sizes. Most OS use 4 kilobytes by default because it's a good balance between memory overhead and translation speed. So the reason why 4 kilobytes are useful, because it's chop of pages in processes allocated is a good balance between overhead and translation speed, kind of like the CFS in a scheduler algorithm and multi-level feedback view. It get the nice fit balance, but again, it still depends on your purpose. So the page size is fixed for the system, not per process. So it's fixed for the system, it's not per process. Okay, so the process will have to adapt with the fixed page size of the system. The number of valid VPNs grows as the process requests more memory. So this virtual private number, or the allocated memory, grows as the process requests more memory. The offset size never changes, like always 12 bits for 4 kilobytes pages. So you just provide the VPN more. You don't change the offset in 4 kilobytes pages. So you may think that every request has a different offset in VPN. No, for 4 kilobytes, it always have 12 offset and 20 VPN that is being converted to PFN. If you want more memory, you just ask for more VPN or virtual private number, as long as there's still free memory on the system. So again, it's being tracked by the process table entry, which is the data structure when boiled down to. So the process asks for the OS memory like malloc in C, system call like BRK or mmap. The OS allocates additional virtual pages for the process. So again, it allocates virtual pages. But virtual pages are included in virtual private number, right? So because the OS tracks that. If those new virtual pages are accessed, the OS maps them to new physical frames. So if those new virtual pages that allocated, because remember it allocated first and then it fetched the instruction, and then if that are accessed by loading a data and the user or the program actually interact with that, the OS maps them to new physical frame to be able to conduct its process, to talk to the CPU. Because again, this architecture, CPU plus MMU, has cache to enable the bits to access that or determine the user program, depending on your operating system and how the data structure and algorithm are processed at the back end, and how the UI interface also are designed in the front end. So example, page size is 4 kilobytes. A process starts with 8 kilobytes of heap. So 2 page sizes. Yeah. Later it allocates 12 kilobytes more. Now heap So 12 kilobytes, that's 3 more pages. Now heap equals to 20 kilobytes. So this heap is now 20 kilobytes. So it started with 8 kilobytes. So you add now 12, now it's 20 kilobyte total. So that needs 5 pages just for the heap. OS updates the page table or the data structure for that per entry table. So 3 new VPNs are marked valid and point to physical prints. So that VPNs or virtual private number will be marked valid on that process table entry. So not to be allocated to other process to avoid overwriting or synchronization problem. So why no valid bit? You may notice that in the Intel example, if there are no separate valid and present bits, but rather just a present bit, if that bit is set p equals to 1, it means the page is both present and valid. If not, p equals to 0, it means that the page may not be present in memory but is valid or may not be valid. An access to a page with p equals to 0 will trigger a trap to the OS. The OS must then use additional structures it keeps to the page from the page table to determine whether the page is valid and thus perhaps should be swapped back in or not, and thus the program is attempting to access memory illegally. This sort of judiciousness is common in hardware, which often just provide the minimal set of features upon which the OS can build a full service. So it's a common to be able to reject by hardware, which often just provide the minimal set of features upon which the OS can build a full service. So the hardware restrict that to the OS, that's why it's common, in which the OS must work on that hardware constraints to be able to serve its purpose or to allocate processes. Paging also too slow. So with page tables in memory, we already know that they might be too big. As it turns out, they can slow things down too. With pages in table memory, we already know that they may be too big. So the page table may be too big. So we don't want that in a physical memory. As it turns out, they can slow things down too. For example, take our example instruction movel 21, %EAX. Again, let's just examine the explicit reference to address 21 and not worry about the instruction fetch. In this example, we'll assume the hardware performed the translation for hash. To fetch the desired, so let's say we're not virtualizing ret the page table, so the hardware are doing that translation. To fetch the desired data, the system must first translate the virtual address 21 into the correct physical address, which is 117. Thus, before fetching the data from address 117, the system must first fetch the proper page table entry from the process page table. So before the system can return the data that it has from 117, which is requested by the virtual address 21, it must first do the step of fetching it from the page table using its page table entry. Perform the translation, so it will perform the translation if it's already have, or if it's not allocated, it will allocate it, and then load the data from physical memory to the user requesting it. To do so, the hardware must know where the page table is for currently running process. So the OS also must track or must know where's the page table allocated for that. So it's additional memory space or additional step. Let's assume for now that a single page table based register contains the physical address of the starting location of the page table. To find the location of the desired PTE, the hardware will thus perform the following functions. So again, let's assume for now that a single page table based register, so page table based register that used to track or contains the physical address of the starting location of the page table. So that single page table register will contain a track or a way to track the physical address of the starting location of the page table or the starting of that page table itself. So to find the location of the, or to use this data structure, again page table is just a data structure, to find the location of desired page table entry, the hardware will thus perform the following functions. So this where the translation are too slow, because this hardware will now have to perform this translation to get that page table entry for this requested process. So VPN equals to virtual address and VPN mask to ship, and PTE address or page table entry address equals to page table based register. So that's what we know so far, plus VPN times size of PTE. So as you can see, we get the VPN, which is the virtual address, and VPN mask, and then the ship or the offset, and then the page table entry of that virtual private number being requested is page table based register plus VPN times size of PTE. So this is another step on its algorithm or the data structure of the page table. So in our example, VPN mask would be set to 0x30 or hex 30 or binary 110000, which picks out the VPN bits from the full address. Ship is set to 4, the number of bits in the offset, such that we move the bits down to form correct integer, such that we move the VPN bits down to form the correct integer virtual page number. So this is the translation that we got earlier, the VPN plus offset. For example, with virtual address 21010101 and masking turns this value, so this is the VPN mask, into 01000. The ship, it turns it into 01 or virtual page 1 as desired. We then use this value as an index into the array of PTEs. So we use that values into this array VPN times size of, pointed by the page table based register, since that's what's the first value we know so far in the data structures. Mask removes the offset and isolates the VPN bits. So this mask removes the offset. So instead of just VPN plus offset, it removes that. Ship moves them down to form an integer VPN. So the ship moves them to form an integer VPN to then get to page table entry. So it has a lot of computation, that's why it takes a lot of time. That VPN is used as an index into the page table array. So this VPN is used as an index in here, page table array. VPN times size of PTE, whose base address is stored in the base page table based register. So we want to extract the VPN mask 0x30 equals to 110000 base 2. So that's how it converts the 0x30 virtual address 0101 base 2. Now when you apply bitwise AND, so it's kind of like an assembly computation, that's why it's hard to conceptualize. VA equals to 21 and mask equals to 0x30 equals to 01000. That's the mask result. Only the VPN portion remains. So 0100. So we have mask, to offset to get the VPN. Now we ship by 4 because the offset is 4 bits. So 01000 base 2 to 4 is 0001 base 2 equals to 1. So that gives us the actual VPN of 1. So that's the result of the computation earlier when converting to the page table entry, or the virtual private number to a physical address. Think of the page table as an array of PTEs. Page table register, PTE 0, PTE 01, PTE 1. So page table, think of that page table register, which is here. base register is like storage or an array of table entry where we track all the table entries. So this is how the OS in its data structure or its code track all the page table entries. So the VPN tell us which PTE to use. So we grab PTE1. Each PTE stores the PFN physical frame number plus flags valid dirty entry. So again, it's go back to the page table entry we discussed earlier, because the VPN 1 tells us which PTE to use. So that's how we convert it via page table, or how we point out where the allocated process is in the page table using page table entry. Since in the register we have all those page table entry, the VPN then tells us which PTE to use. So this VPN, which is initially we use an offset or bitwise end using its mask and an actual virtual address. So we combine that, we use that VPN to be able to get the PTE exact address using the PTE base register and its VPN. So the VPN tells us which PTE to use included with the page table register. So we grab PTE1. Each PTE stores the PFN physical frame number plus valid flags, dirty, etc. on the actual memory. So that's actually how the hardware and the OS combines to be able to provide this access, the cache, the user mode, the functions, etc. to our calling program. Suppose PTE1 says VPN1 suppose that the PTE1 from the base address, that base register address says VPN1 is in physical frame number 7. So PFN 111, which is its base 2 plus offset 01012, its physical address is 1110101 base 2 equals to 1117 base 10. So once this physical address is known, the hardware can fetch the PTE from memory. So we already know where it's physically. Now the hardware will fetch the PTE or the entry table from memory, extract the PFN. It will now extract the physical frame number, the actual data. So notice it start with the table entry before you get the actual data from the physical frame number, and concatenate it with the offset from the virtual address to form the desired physical address. So the hardware will concatenate that with the offset that we got earlier to get to the exact physical address. Specifically, you can think of PFN being left shifted by shift, and then bitwise OR with the offset to form the final address. So think of that the physical frame number as being offsetted like the VPN converted earlier, and then a bitwise OR with the offset to form the final address like the bitwise end or bitwise end or bitwise OR to get the final address as follows. So offset equals the virtual address and offset underscore mask, and fis address equals to PFN to ship or offset. So step by step example, movel 21 percentage EAX, virtual address provided by the program, VA equals to 21 base 10 plus 010101 base 2. Extract VPN and offset. VPN is equals to VA and VPN underscore mask to ship. Mask is 0101 base 2 and 110000 base 2 equals to 010000 base 2. Shift right to 4, which is 01 base 2 equals to 1. Offset V equals to VA and offset underscore mask equals 0101 base to 2 equals to 5. Locate page table entry PTE. PTE address equals to PTE PT base register plus VPN times size of PTE. So use the page table base register as the starting address. So we use the recorded base register just like the PTE0, PTE1, depending on its page table entry. Add the VPN1 times the PTE size points to PTE1. So now we will add the VPN1 since we convert the VPN, it's equated to 1, which we got from here. Shift right to 4, 0, 1 base to 10 equals to 1. So that's mask for VA and VPN mask to ship. So that's how we get the VPN. So VTBR, so add the VPN1 times the PTE size, so 0.2 PTE1. So that's 1 VPN and the size of PTE. So PTE, open and close, square bracket, 1. Fetch the PTE. So PTE is equals to access memory, PTE address. So the page table entry is equals to access memory, the actual physical or PTE address. Suppose PTE1 says PFN equals to 111 base 2 equals to 7, valid equals to 1. So check validity and protection. If PTE.valid equals to false, raise segmentation fault. Else if protection bit disallow access, raise protection fault, else continue. So that's the code in this data structure. This is how it does the PTE.valid, and it's also how this page table entry works with accessing the page table and converting it to physical address. So again, suppose PTE1, so let's say we have PTE equals to access memory. We're now accessing the PTE address we just computed from the previous data structure. Suppose PTE1 says PFN equals to 111 base 2 equals to 7. So valid equals to 1. Let's say we get this like the 21 entered, right, in the 117. So it says valid. So it checks the validity protection first. If PTE.valid equals to false, raise segmentation false. So this is the code. Else if protection bit disallows access, raise protection fault, else continues. From the physical address, so phys address equals to PFN less than shift or offset. PFN equals to 7 equals 111 base 2. 111 less than 4 equals to 1110000 base 2 equals to 112. Or with offset 0101 base 2 equals to 5. 1110101 base 2 equals to 117. So or with offset, so that's the result. First, the 111 less than 4 is equals to 111, which is 1112. So PFN to 1112 or offset, or with the offset 01012 equals to 5, which is the 117. So that's where the actual physical address. We got first the PFN, the 111, and the offset of 5 plus 5 is equals to 16. We have 111, we shift it by 4 equals to 111000 base 2 equals to 112. Now with an OR with offset, we just need to add 5 for that to get the actual physical address. Plus 5 equals to 117. So as you can see, we shift it, the PFN and then shift are used to calculate the 112. But we can definitely see that in the graph already when we divided that by 8 frames, right? But in here, we just see how it looks like in the code or in data structure, how it is being implemented. So so now access physical memory register equals to access memory, the physical address, fetch data at PA equals to 117, loads it into percentage EAX. So it fetched first the data at 117 and it loads the data. Final line. Finally, the hardware can fetch the desired data from memory and put it into register EAX. So the hardware can now fetch the data, desired data from memory and put it into the register EAX of the CPU to be able to execute it. So it's been a long way for the memory, just for it to be able to load that or to execute that in CPU. That's why we need to solve a bigger problem using this same data structure of page table using access bit to optimize this memory allocation. So the program has now succeeded at loading a value from memory. So key observation from figure 18.6. For every single memory reference, load, store, or instruction fetch, you must first read the page table. So extra memory access. If you reference just load, even just instruction fetch, you need to first read the page table, which extra step from memory. Again, this is how the data structure and algorithm time complexity come. It's how the memory are being used. So first it reads page table from memory, then you can fetch the actual data. This doubles the cost of memory access or worse, which is why paging by itself is too slow and motivates optimization like TLB, which is translation look side buffer. So it first read, that's the first step in the page table, then you can fetch the actual data to the program. It's kind of like a two-step. So the ship plus OB trick is just a fast bitwise way of concatenating. So that's a bitwise way or the assembly ways of concatenating the instruction to the CPU. Concatenating PFN and offset. PFN gives the page frame base address. So PFN gives the asterisk asterisk page frame base address asterisk asterisk, and offset tells you where inside that frame. So PFM is the base and the offset where it's at. Finally, the hardware can fetch the desired data from memory and put it into register EAX. The program has now succeed at loading a value from memory. So to summarize, we now describe the initial protocol for what happens on each memory references. So that's the data structure or an algorithm on each memory references of OS. Figure 18.6 page 9 shows the approach. For every memory reference, whether an instruction fetch or an explicit load or store, paging requires us to perform one extra memory reference in order to first fetch the translation from the page table. That is a lot of work. Extra memory references are costly, and in this case will likely slow down the process by a factor or 2 or more. So here, extract the VPN from the virtual address. VPN equals the virtual address and VPN mask, and ship from the address of the page table entry PTE. PTE address equals to PTB base register plus VPN times size of PTE. Then now after we access that page table address, entry address, we fetch the PTE equals the access memory PTA address. So because that PTE will determine how that actual PTE address can be accessed, whether it's valid or not. So check if process can access the page. So this is the actual if-else code of the data structure. If PTE.valid equals to false, raise exception segmentation fault. Else if can access PTE.protect bits equals to false, raise exception protection fault. Else access OK from physical address and fetch it to the program. Then offset equals to virtual address and offset mask. So it calculates the offset, which is the virtual address, and the offset mask we calculated at the above code. Physical address equals to pte.pfn less than pfn ship, or offset. Register equals to access memory, the physical address. Accessing memory with paging. So that's how we access memory with paging. And now you can hopefully see that there are two real problems that we must solve. Without careful design of both hardware and software, page tables will cause the system to run too slowly, as well as take up too much memory. So it will run slowly and then take memory without careful design of this page table virtualization of data structure and algorithm. So again, it's just a data structure. While seemingly a great solution for our memory virtualization needs, these two crucial problems must first be overcome. Memory trace. So before closing, we now trace through a simple memory access example to demonstrate all of the resulting memory access that occur when using paging. The code snippet in C in a file called array.c that we are interested in as follows. So int array with a parameter input 1000 semicolon for I equals to 0 semicolon I less than 1000 semicolon I plus plus REI equals to 0 semicolon. Then we compile RE.c and run it with the following commands. In the prompt, gcc dash o space dash o space re.c dash wall dash o, then prompt dot slash re to execute it. Of course, to understand what memory access this code snippet, which simply initialize an array, we'll have to know or assume a few more things. First, so in order to understand it, we need to assume first things. So first, we'll have to disassemble the resulting binary using objdump on Linux or otool on a Mac to see what assembly instructions are used to initialize the array in a loop. Here is the resulting assembly code. So we use that prompt or the command to see what assembly code are used to execute that array. So here 1024 move L $0x0 comma open parenthesis percentage EDI comma percentage EAX comma 4 closing parenthesis one, and then enter 1028 space INCL space percentage EAX, and then in 1032 CMPL space $0x03E8 comma percentage EAX, and 1036 space JNE space 1024. The code, if you know a little x86, is actually quite easy to understand. The first instruction moves the value 0 shown as $0x0 into the virtual memory address of the location of the array. So it's this first instruction move the value 0 into the virtual memory address of the location of the array. So it moves the 0 value is moved into the location of the array. This address is computed by taking the contents of percentage EDI and adding percentage AX multiplied by 4 to it. Thus, percentage EDI holds the base address of the array, whereas percentage EAX holds the array index I. Thus, percentage EDI holds the base address of the array, whereas percentage EAX holds the array index. So this EDI of the assembly, it holds the base address, or where that virtual address of the array, and then as percentage EAX holds the array index, we multiply by 4 because the array is an array of integers, each of size 4 bytes. So that is the percentage EAX of assembly holds the actual index of the array, and we multiply that by 4 because it's an array of integers, each of size 4 bytes. So that integers are size 4 bytes. So the second instruction increments the array index held in percentage EAX. So 1028 space INCL percentage EAX. So that's where the incrementation of the assembly code. And the third instruction compares the content of that register to the hex value 0x03E8. So 1032 CMPL, so that's kind of like the compare in assembly, or decimal 1000. It compares that to the hex value or the decimal 1000. If the comparison shows that the two values are not yet equal, which is what the line instruction tests, the fourth instruction jumps back to the top of the loop. So 1036 or the fourth line space GNE space 1024. That is the assembly line that moves back to the loop. To understand which memory access this instruction sequence makes at both the virtual and physical levels. So again, to understand which memory accesses this instruction sequence makes at both the virtual and physical levels. So again, to understand which memory accesses this instruction sequence makes at both the virtual and physical, which is the conversion of VPN to PFN, we'll have to assume something about where a virtual memory, the code snippet, and array are found. So we need first to assume where in the virtual memory is that code snippet of the array are found, as well as the contents and the location of the page table in the physical memory. For this example, we assume a virtual address of size 64 kilobytes, unrealistically small. We also assume a page size of 1 kilobytes. All we need to know are the contents of the page table and its location in physical memory. Let's assume we have a linear array-based page table. Let's say we use a array linear page data structure in a page table, and that it is located at physical address 1 kilobytes 1024. So let's assume that it's located in the actual content, which is the 1 kilobytes of this code. As for its contents, there are just a few virtual pages we need to worry about having mapped for this example, because the content is too small, just 1 kilobytes. First, there is the virtual page the code lives on. Because the page is 1 kilobytes, virtual address 1024 resides on the second page. So because the page size is 1 kilobytes, virtual address 1024 resides on the second page of the virtual address space, which is VPN equals to 1 as VPN equals to 0 is the first page. So the code lives on the first page. And because the page size, which is virtual as, is actually on the second page, so let's assume a virtual page, kind of like the header and the actual allocated. You have the size to track the allocated space and the actual space. So let's assume this virtual page maps to physical frame 4, VPN to PFN4. Next, there is the array itself. Its size is 4000 bytes or 1000 integers, and we assume that it resides at virtual address 4000 through, so again we made an assumption, 40,000 through 44,000, not included because it's 4000 bytes, not including the last byte. The virtual pages for this decimal range are VPN equals to 39 to VPN equals to 42, because each page is 1000, right? 39, 40, 41, 42. Thus, we need mappings for these pages. Let's assume this virtual to physical mappings for the example. VPN 39, PFN 7, VPN 40, PFN 8, VPN 41, PFN 9, VPN 42, PFN 10. We are cheating a little bit here, assuming each instruction is 4 bytes in size for simplicity. In actuality, x86 instructions are variable size. So here's an example: page table 39, 1224, page table 1 to 124. The array 4100 to 40,050 to 40,100. The code 1074 to 1124, etc. So that's the memory access, different x and y axis. We are now ready to trace the memory reference of the program. So this is how the data structure of this linear page table track the memory reference of the program. When it runs, each instruction fetch will generate 2 memory references, one to the page table to find the physical frame that the instruction resides within, and one to the instruction itself. So again, one to the physical frame that the instruction resides, or the data of that instruction, and one to the instruction itself, kind of like the header in the allocated space, to fetch it to the CPU for processing. In addition, there is one explicit memory reference in the form of move instruction. So again, in addition, there is one explicit memory reference. So aside from those two, there is one explicit memory reference in the form of move instruction from the assembly. This adds another page table access first to translate the virtual address to the correct physical one, and then the access itself. So it requires or adds another page table access first to translate the array virtual address to the correct physical one, and then the array access itself. The entire process for the first 5 loop iterations is depicted in 18.7 page 11. So this the as you can see, this data or the access, this is how it is depicted in different graphs. As you can see, we have a different pages in the memory. Some are in the 4000, some in the page table. So that's how it was able to keep this free space destroyed. So the bottommost graph shows the instruction memory reference on the y-axis in block, with virtual addresses on the left and the actual physical addresses on the right. The middle graph shows array access in dark gray, again with virtual on left and physical on right. Finally, the topmost graph shows page table memory access in light gray, just physical, as the page table in this example resides in physical memory. Here you don't have an x and y axis, as the page table in this example resides in the physical memory. So this is the actual physical memory. So you can see, as we have this conversion, we have a different graph. The x-axis for the entire trace shows memory access from the first 5 iteration of the loop. There are 10 memory access per loop, which includes 4 instruction fetches, 1 explicit update of memory, and 5 page table access to translate those 4 pages, and 1 explicit update. So there's a lot of steps. 4 instruction fetches, 1 explicit update of memory, and 5 page table access to translate those 4 fetches and 1 explicit update. So that is how this linear page data structure works in terms of time complexity. See if you can make sense of this pattern that show up in this visualization. In particular, what will change as the loop continues to run beyond these 5 iterations? Which new memory locations will be accessed? Can you figure it out? This has just been the simplest of example, only a few lines of C code, and yet you might already be able to sense the complexity of understanding the actual memory behavior of real application. Don't worry, it definitely gets worse, because the mechanism we are about to introduce only complicate this already complex machinery. We have introduced the concept of paging as a solution to our challenge of virtualizing memory. Paging has many advantages over previous approaches, such as segmentation. First, it does not lead to external fragmentation, as paging by design divides memory into fixed units. Second, it's quite flexible, enabling the sparse use of virtual address spaces. So as we can see in that code, that's how actually it disperses. So this form of virtualizing memory, it disperses that in different physical memory address. So it's some are in this virtual address, or let's see, some are in 400146 to 4196, some are in 7282 to 7332 in physical address, but in virtual address we allocate that as a 40,000. Some only has the physical address, which is the page table. So as the loop expands, as you can see, we have this different movement of data, which makes it complicated. Again, first, it does not lead to external fragmentation, as paging by design divides memory into fixed size units. Second, it is quite flexible, enabling the sparse use of virtual address spaces. However, implementing paging support without care would lead to slower machine, with many extra memory access to access the page table, as well as memory waste, with memory filled with page tables. So without care, it could lead to slower machine with extra memory access to the page table, because again, it needs to access page table every time, as well as memory waste with memory filled with page tables instead of useful application data. So instead of the actual processes, it could be scattered by this page table if we're not careful, or this memory of just accessing page table, because again we need a translation for each process if we're not careful. We'll just have to think a little harder to come up with a paging system that not only works but works well. The next two chapters fortunately will show us how to do so. So paging, faster translation, TLBs. So using paging as the core mechanism to support virtual memory can lead to high performance overheads. By chopping the address space into small fixed units like pages, paging requires a large amount of mapping information. Because that mapping information is generally stored in physical memory, paging locally requires an extra memory lookup for each virtual address generated by the program. Going to memory for translation information before every instruction fetch or explicit load. So we just discussed the explicit load earlier, but it actually has to do it with instruction as shown in different sparse loop addresses in the array that we discussed. When we want to make things fast, the OS usually needs some help. So if you want to make this fast, the OS needs some help. And help often comes from the OS old friend, the hardware. So again, we were going to use the cache again, that access bit, to create this algorithm. To speed address translation, we're going to add what is called, for historical reasons, a translation look aside buffer, or TLB. A TLB is a part of the chip's memory management unit, MMU. So again, it's is designed, or CPU in modern architecture such as x86 in CPU and MMU, which is a translation look aside buffer, or a TLB. So a TLB is already part of the MMU, and is simply a hardware cache of popular virtual to physical address translations. So kind of like as well the cache in the multiprocessor access. So this is where we track the access bits already accessed, and or valid or invalid, and protection data structure. Really, it's just a data structure that are afforded to us by the hardware, but it's still, again, it's restricted, but the OS can make way to, or make do with those available x86 options, such as being able to communicate on that using that if-else protection and segmentation fault, and converting that to an actual assembly that the CPU can actually understand. So this is supported to us by hardware. So a hardware cache of popular virtual to physical address translation. Thus, a better name would be an address translation cache. Again, address translation cache. So this is also what we used in CPU cache in a multiprocessor. Upon each virtual memory reference, the hardware first checks the TLB to see if the desired translation is held therein. So it checks that in or this TLB before accessing the real memory. If so, the translation is performed quickly without having to consult the page table, which has all translation, or the page table which has all translation, kind of like a page table before the actual page table. Because of this, their tremendous powerful performance impact, TLBs in a real sense make a virtual memory possible. So because of that tremendous impact, this is what actually the innovation that makes this illusion of virtual memory possible. So the crux, how to speed up address translation. How can we speed up address translation and generally avoid the extra memory reference that paging seems to require? Again, how can we speed up address translation and generally avoid the extra memory reference that paging seems to require. So how can we speed up the address translation instead of using a page table and avoid that extra memory reference that this paging data structure or linear page data structure seems to require? What hardware support is required? So these are the answer. A TLB flow control flow algorithm. So there's already that capability of exception or the protection fault and the access using the TLB hit in the CPU and memory. We just need to implement this in our OS. So a TLB basic algorithm. I think we have to copy this. So figure 19.1 shows a sketch of how hardware might handle a virtual address translation, assuming a simple linear page table. So let's say you have a linear page table. You're gonna save this in this simple linear page table that already implemented in the paging earlier. We're gonna add this code into the hardware so that we can talk or activate that hardware functionality, which is the TLB cache. So might handle a virtual address translation assuming a linear page table, like the page table is an array in a hardware managed TLB, like the hardware. So let's say the page table is a simple data linear array and hardware managed TLB, like the hardware handle much of the responsibility of page table accesses. So it handles that page table accesses basically. We'll explain more about this below. The algorithm the hardware follows works like this. First, extract the virtual page number from the virtual address line 1 in figure 19.1. So again, it's the same as before. It gets the virtual page number, virtual address, and VPN mask to ship, and then success, comma, TLB entry equals to TLB lookup. And check if the TLB holds the translation for this VPN line 2. So this TLB implementation of hardware are being used here by this linear page table now. So success, comma, TLB entry equals to TLB lookup VPN. We're basically checking if that part of the hardware, we're gonna activate or gonna use that part of the hardware in this page table code that we're gonna use to be able to find that program or to access that program easily. And check if the TLB holds the translation for this VPN line 2. If it does, we have a TLB hit. So if success equals to true, / TLB hit, which means the TLB holds the translation. Success, we can now extract the page frame number from the relevant TLB entry. So if that TLB holds it, again it's a small cache by the CPU. Again, it's small because if it's big, it loses its efficiency, just like we discussed in the previous video. If it does, we have a TLB hit, which means the TLB holds the translation, which means we don't need to access the page table. Success, we can now extract the page frame number, PFN, from the relevant TLB entry. Concatenate that into the offset from the original virtual address. So yeah, if success equals to true, such that TLB, if can access TLB entry that protect bits. So this is the protect bits of the page table entry equals to true. Offset equals to virtual address and offset mask. Piece address equals to TLB entry that PFN to shift or offset. Then register equals to access memory the physical address. So this is the code for accessing that. We're just activating that it's already activated in this x86 CPU plus MMU architecture. Concatenates that all to the offset from the original virtual address and form the desired physical address and access memory lines 5 to 7. So here 5 to 7. Assuming protection checks do not fail, which is line 4. So physical address, sorry, what line is that? Yeah. If it doesn't violate the protection bits which we have in its table entry. So if this is true, therefore we can access. If not, we'll implement this race exception. If the CPU does not find the translation in the TLB, a TLB miss, we have some work to do. In this example, the hardware accesses the page table to find the translation, lines 11 to 12. And assuming that virtual memory references generated by the process is valid and accessible, lines 13 to 15. So again, if the CPU does not find the translation in the TLB, which is miss, we have some work to do. In this example, the hardware accesses the page table to find the translation 11 and 12. So else PTE addresses, so it accesses the page table which is lower, equals to PTBR plus VPN times size of PTE, which is the code we used to access earlier in the paging. PTE equals to access memory PTE address. Again, we use a VPN times size of PTE, and we use a beast register. And assuming that the virtual memory reference generated by the process is valid and accessible, lines 13 and 15. So if PTE.valid equals to false, so we will also implement that exception in the valid, like in the page table when we use the when we access the page table. So updates the TLB with the translation line 18. So again, and assuming that the virtual reference generated by the process is valid in here, if PTE.valid equals to false, and accessible, lines 13 to 15, raise exception, segmentation false, else if can access PTE.protection bits equals to false, raise exception, protection false, else TLB insert VPN PTN.pfn, PTE.protect bits, then retry instruction. So generated by the process is valid and accessible, lines 13 to 15, updates the TLB with the translation line 18. So TLB insert, so it will let's say it's valid and not it's also not protected. It will update the TLB, which is the cache, with the translation in line 18, which is TLB insert VPN, PTE.pfn, PTE.protection bits. Notice the code used here that can be communicated to the assembly, which is the insert. So this is a C language that can be used to insert to the actual hardware cache. So this set of actions are costly primarily because of the extra memory reference needed to access the page table, line 12. Finally, once TLB is updated, the hardware retries the instruction. So we use C retry instruction to communicate to the hardware, and it will be accepted by the CPU. This time the translation is found in the TLB and the memory is processed quickly. So again, it tries the instruction since it's already in the cache. Therefore, the process can be responded to quickly. So the interactivity of this virtual memory is not compromised, along with the scheduler, of course. A good scheduler that optimized for your workload. The TLB, like all caches, is built on the premise that in the common case, translation are found in the cache, are hits. So it builds on the assumption, like in the about face design, that most of the things that we access are actually the things that we most likely will be accessed, or the common features that we use, will also be likely that is most frequently accessed, because we are a creature of habit. That's why this works, because of that assumption, because of that fact with our psychology. If so, little overhead is added, as the TLB is found near the processing core. So that TLB is activated or found in the near the processing core, or the CPU, and is designed to be quite fast. Again, it's designed to be quite fast because it's a cache. When a miss occurs, the high cost of paging is incurred. The page table must be accessed to find the translation, and an extra memory reference or more with more complex page tables results. If this happens often, the programs will likely run noticeably more slowly. More memory access relative to most CPU instructions are quite costly, and TLB misses led to more memory access. Thus, it is our hope to avoid TLB misses as much as we can. So these are the key. This virtualizing of memory works with how the CPU caches it, or the modern scheduler works. So basically, most of the things that is being run on our operating system now is being run in a cache. That's why it is able to make it faster, or make the interactivity faster. So this is where the innovation of computers. So example, accessing an array. To make clear the operation of a TLB, let's examine a simple virtual address trace and see how a TLB can improve its performance. In this example, let's assume we have an array of 10 4-byte integers in memory, starting at virtual address 100. So let's say we have a 4-byte, 1, 2, 3, 4. Starting at virtual address 100. Assume further that we have a small 8-bit virtual address space. So again, it's determined by the system, right? The size of our page with 16-byte pages. Thus, a virtual address breaks down into a 4-bit VPN. There are 16 virtual pages and a 4-bit offset. There are 16 bytes on each of those pages. So there's a 16 bytes on each of these pages. And we have this 10 4-bytes, 0, 1, 2, up to 9. So this is an example of an array that is being executed, for example. So here is the TLB control flow algorithm. So these are the things that we discussed earlier. So figure 19.2 shows that the array layout on the 16-byte pages of the system. So it's a 16-byte because each page has this 4 bytes, 16 bytes pages. As you can see, the array's first entry, A0, begins on VPN equals to 6 offset 4. So here VPN equals to 6 and then offset 4. It's not on offset 0 or offset 8 or offset 12 or offset 6. Only 3 4-byte integers fit onto that page. The array continues onto that next page, VPN equals to 7, where the next 4 entries, A3 to A6, are found. Finally, the last 3 entries of the 10 entry area, 8 to 7 to 89, are located on the next page of the address space, VPN equals to 6. Now let's consider a simple loop that accesses each array element. Something that would look like this in C. So we run this and then we convert it in assembly in pages. Now let's try if we now activate that hardware algorithm in page table. So what would the performance would be? Now a simple change in page table algorithm like that. What would be this performance would be? For the sake of simplicity, we will pretend that the only memory accesses the loop generates R to the RE. Ignoring the variables. So let's ignore the variables and sum as well as the instruction themselves. Only the load as well. So let's forget the instruction, the RE, and the sum or the operation. So when the first array element A0 is accessed, the CPU will see a load to virtual address 100. So that CPU page table algorithm we created along with the help of the CPU will see a load to virtual address 100. The hardware extract the VPN from this, which is VPN equals to 06 when it converted it, and uses that to check the TLB for a valid translation. So it see that it's a VPN equals to 06 or virtual page number equals to 06 and check if it's already in the cache. Assuming this is the first time program access the array, the result will be a TLB miss. So in that, based on that TLB control flow, it will be missed. The next access to O1, and there is some good news here. A TLB hit because the second elements of the array is packed next to the first. It lives on the same page. So because it lives on the same virtual private number or the same page, because we're already accessed this page when accessing the first elements of the array, the translation is already loaded into the TLB, and hence the reason for our success. Access to a O2 counters similar success, another hit, because it too lives on the same page, A0 and A1. Unfortunately, when the program accesses A3, we encounter another TLB miss. However, once again, the next entries, A4 and A6, will hit in the TLB, as they all reside on the same page in memory, in the physical memory. So again, just because of the page size of the virtual memory is only 4 bytes does not mean that that is the page size in the actual memory. So the page size in the actual memory will determine how the TLB will access that, because that page kind of like has the same processor or cache in it. So that physical page, part of that physical frame page is already accessed. Therefore, all of that pages, virtual memory pages, will be accessed as well in that same physical memory because of that power of cache or that processor designed to do that. So finally, access to A7 causes one last TLB miss. The hardware once again consult the page table to figure out the location of this virtual page in physical memory. So again, finally, access to A7 causes one last TLB miss. The hardware once again consult the page table to figure out the location of this virtual page in physical memory and update the TLB accordingly and retry instruction. So that's the algorithm. You put that into the TLB and retry instruction and access it using TLB first. So the if-else statement or the flow algorithm are designed to access the TLB first before accessing the physical memory to avoid this problem of paging. So this is how we solve the paging problem. The final two accesses, A8 and A9, receive the benefits of this TLB update. When the hardware looks in the TLB for this translation, 2 more hits result, because again, the TLB is being updated based on the physical frame page, not on the page size of the virtual page number. So let us summarize TLB activity during our 10 accesses to the array. Miss, hit, hit, miss, hit, 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 miss, hit, hit. Thus our TLB hit rate, which is the number of hits divided by the total number of accesses, is 70%. Although this is not too high, indeed we desire hit rates that approach 100%, it is not non-zero, which may be a surprise. Even though this is the first time the program accesses the array, the TLB improves performance due to spatial locality. So that's the concept of cache. Again, it's the same with the CPU cache we described in the previous video. The elements of the array are packed tightly into pages, like they are close to one another in space, and thus only the first access to an element on a page yields a TLB miss. Also note that the page size placed in this example, if the page size of the frame or the physical frame is huge, like twice as big, like 32 bytes, not 16, the array access would suffer even fewer misses. A typical page sizes are more like 4 kilobytes. These types of dense array-based accesses achieve excellent TLB performance, encountering only a single miss per page of access. So when we increase that physical page frame, and we know that the typical page virtual page size is 4 kilobytes, we only encounter a single miss per page of accesses. One last point about TLB performance: if the program soon after this loops completes accesses the array again, we'd likely see an even better result, assuming that we have big enough TLB to cache the needed translations. So after you access, that's why the program that your memory or your system accesses is faster the second time. The reason for that is because of the cache. It's already accesses that in the CPU, and most of the modern operating system use this cache or activate this cache for faster provision of that space for the process. So we'd likely see an even better result, assuming that we have a big enough TLB, from the CPU. So if your CPU has a high enough TLB to cache the needed translation, like hit in this case. So the TLB hit rate will be high because of temporal locality, the quick referencing of memory items in time. Like any cache, TLBs rely both on spatial and temporal locality for success, which are program properties. So if the program of interest exhibits such locality, and many programs do, the TLB hit rate will likely be high. So tip: use cache when possible. Caching is one of the most fundamental performance techniques in computer systems, one that is used again and again to make common case fast. The idea behind hardware caches is to take advantage of locality in instruction and data references. There are usually two types of locality: temporal locality and spatial locality. With temporal locality, the idea is that an instruction or data item that has been recently accessed will likely be reaccessed soon in the future. Think of loop variables or instructions in a loop. They are accessed repeatedly over time. With spatial locality, the idea is that if a program accesses memory at address X, it will likely soon access memory near X. Imagine here streaming through an array of some kind, accessing one element and then the next. Of course, these properties depend on the exact nature of the program and thus are not hard and fast laws, but more like rules of thumb. Hardware caches, whether for instructions, data, or translations, as in our TLB, so whether it's for instruction, data, or address translation, or loading, which is the address translation, data or instructions, take advantage of locality by keeping copies of memory in small fast on-chip memory. So this actually is a CPU plus MMU, which is the keeping the copies of memory or the actual physical memory in a fast on-chip memory alongside with the CPU. It's a small, but it is designed that way to be able to serve fast. Instead of having to go to a slow memory to satisfy a request, the processor can first check if a nearby copies exist in a cache. If it does, the processor can access it quickly in a few CPU cycles and avoid spending the costly time it takes to access memory, many nanoseconds. You might be wondering, if caches like TLB are so great, why don't we just make bigger caches and keep all our data in them? Unfortunately, this is where we run into more fundamental laws like those of physics. If you want a fast cache, it has to be small, as issues like the speed of light and other physical constraints become relevant. Any large cache, by definition, is slow, and thus defeats the purpose. Thus, we are stuck with small, fast caches. The question that remains is how to best use them. Who handle TLB misses? One question that we must answer: who handles TLB misses? Two answers are possible: the hardware or the software, OS. In the olden days, the hardware had complex instruction set, sometimes called CISC for complex instruction set for computers. So who handled that TLB miss? In the olden days, it's actually the hardware using the complex instruction set, sometimes called CISC for complex instruction set computers, and the people who built the hardware didn't much trust those sneaky OS people or the writer of operating system. Thus, the hardware would handle the TLB miss entirely. So just like we had the code earlier, like the few constraints by the hardware and the OS people make do of that. To do this, the hardware has to know exactly where the page tables are located in memory via page table based register used in line 11 in figure 19.1. So we used that code earlier by checking the base register used in that previous code, as well as the exact format on a miss. The hardware would walk the page table, find the correct page table entry, and extract the desired translation, updates the TLB with translation, and retry the instruction. An example of an older architecture that has hardware managed TLBs is the Intel x86 architecture, which uses fixed multi-level page table. So this is where you can use that code in this x86 old architecture or Intel, which use a multi-level page table. So these are the multi-level page table that we discussed that could be alternative on that single line array page table in the previous inefficient paging example. Now this is the that is the previous version. So this is how it looks like: linear page table, multi-page table. So it accesses memory differently as shown in this graph. So this multi-level use the hardware to optimize the access using TLB. So more modern architectures like MIPS R10K or Sans Spark version 9, both RISC or reduced instruction set computers have what is known as software managed TLB. So in a modern architecture, you can now manage that cache using a software, and it is being managed by software, and it has fewer codes. On a TLB miss, the hardware simply raises an exemption. In line 11 in figure 19.3, here, raise exemption TLB miss, which pauses the current instruction stream, raises the privilege level to kernel mode, and jumps to a trap handler to access the page table. So it jumps to a trap handler or raises the privilege mode to access the actual page table. Notice how that is the same in page table and how we access the system call. That's also where we register that memory access to memory page table to be able to access that data for first access for that memory if it is not on the cache yet. As you might have guessed, this trap handler is code within the OS that is written with the express purpose of handling TLB misses. When run, the code will look up the translation in the page table, use special privilege instruction to update the TLB, and return from trap. At this point, the hardware retries the instruction, resulting in a TLB hit. So let's try to unpack this. VPN equals the virtual address and VPN mask to shift again. So it's a common C way to virtualize memory. Success, TLB entry equals to TLB lookup with the argument VPN. If success equals the true, TLB hit. If can access, TLB entry that protected bits equals to true. Then offset equals to virtual address and offset mask. Physical address equals to TLB entry that PFM less than shift or offset. Register equals to access memory physical address. Else raise exception protection fault. Else raise exception TLB miss, and then it's just handle it again. So it uses special privilege instruction to update TLB and return from trap. At this point, the hardware retries the instruction, resulting in a TLB hit. Let's discuss a couple of important details. First, the return from trap instructions needs to be a little different from the return from trap we saw before when servicing a system call. Again, so let's discuss a couple of important details. First, the return from trap instruction need a little different from return from trap we saw when servicing a system call before in the hardware. In the latter case, the return from trap should resume execution at the instruction after the trap into the OS, just as a return from a procedure call return to the instruction immediately following the call into the procedure. So just like a system call, when you raise exception, you activate the privilege mode into the OS. In the former case, when returning a TLB miss from a TLB mishandling trap, the hardware must resume execution at the instruction that caused the trap. This retry thus lets the instruction run again, this time resulting in a TLB hit. Thus, depending on how a trap exception was caused, the hardware must save a different PC when trapping into the OS. So depending on what algorithm we use, the hardware must save a different program counter when trapping into the OS in order to resume properly when the time do so arrive. So aside RISC versus CISC, in the 1980s, a great battle took place in the computer architecture community. One side was the CISC which stood for Complex Instruction Set Computing. On the other side was RISC for Reduced Instruction Set Computing. The RISC was spearheaded by David Patterson at Berkeley and John Hennessy at Stanford, who are also co-authors of some famous books. Although later John Koch was recognized with the Turing Award for his earliest work on RISC, CISC instruction set tends to have a lot of instruction in them, and each instruction is relatively powerful. For example, you might see a string copy which takes 2 pointers and a length and copies bytes from source to destination. The idea behind CISC was that instructions should be high-level primitives to make the assembly language itself easier to use and to make code more compact. RISC instruction sets are exactly the opposite. A key observation behind RISC is the instruction sets are really compiler targets, and all compilers really want are a few simple primitives that they can use to generate high-performance code. Thus, RISC proponents argued, let's rip out as much from the hardware as possible, especially the microcode, and make what's left simple, uniform, and fast. In the early days, RISC chips made a huge impact as they were noticeably faster. Many papers were written, a few companies were formed, MIPS and Sun. However, as time progressed, CISC manufacturers such as Intel incorporated many RISC techniques into the core of their processors. For example, by adding early pipeline stages that transform complex instruction into micro instruction, which can then be processed in a RISC-like manner. These innovations, plus a growing number of transistors on each chip, allowed CISC to remain competitive. The end result is that debate died down, and today both types of processor can be made to run fast. Second, when running the TLB handling code, the OS need to be extra careful not to cause an infinite chain of TLB misses. So the OS need to be careful to not run an infinite TLB misses. Many solutions exist. For example, you could keep TLB miss handlers in physical memory where they are unmapped and not subject to address translation, or reserve some entries in the TLB for permanently valid translations and use some of the permanent translation slots for the handler code itself. These wide translations always hit in the TLB.